In continuing our lesson about analyzing graphs, we're going to talk about minimum and maximum points on a graph. Point A on the graph is a relative maximum of the function since no other points have a greater y coordinate. So as I look at point A on the graph, I see that it's kind of at the top of a hill, so it's referred to as a relative maximum. And the reason it's relative maximum and not just maximum is because it's actually not the highest point on the graph. Because we can see that the arrow is going to continue to make this graph rise higher, higher, higher. And so A is not really the highest point in the graph, but we consider it a relative maximum because it's higher than any of the points surrounding A on the graph. Likewise, point B on the graph could be considered a relative minimum. So point B right here is a relative minimum because it is a low point on the graph. It's kind of in a valley on the graph. The general term for relative maximum and relative minimum values is called extrema. So if you see extrema, they're talking about maximum and minimum values. And then the last thing is that both the maximum and the minimum values are called turning points simply because that's where the graph turns. The graph of the polynomial function of n degree n has at most n minus 1 turning points. Another way of putting that is that if you count the number of turning points and add 1, you're going to get the degree. So number of turning points plus 1 equals the degree of the function. So we're going to get several different questions here today. First off, we're going to graph f of x equals x cubed minus 4x squared minus 2x plus 3. And you're going to do so by using Desmos. So go to Desmos at desmos.com and type in that equation. Okay, so I've already typed in that equation, and you can see the graph goes upward and then back downward and then back up again. Now, sometimes you will have to move your graph around so you can see both of the turning points, or you might have to zoom in or zoom out on your computer to see everything. But again, Desmos is very good about helping you answer some of the questions on it. So the next question that we're going to answer was, estimate the x-coordinate of every turning point and determine if those coordinates are relative maximum or relative minimums. So Desmos is very good about estimating those relative maximums or minimums if you just touch close to those points. And you can see when I touch the points that it starts to highlight some very important points. And there's a relative maximum or a high point right there. And the x value of that is negative 0.23. So the answer for a relative maximum, the x value would be negative 0.23. And if you touch towards the bottom of the graph, you can see that the x value of a relative minimum, because that's a low point in the graph, is 2.897. The next question was, determine the smallest possible degree of the function. So notice that there were two turning points. There was a turning point at the relative maximum and a turning point at the relative minimum. So that's two turning points, but to find a degree, you would add the number of turning points plus 1, which means it has a degree of 3. And then finally, the last question was, determine the domain and the range of the function. So notice the graph continues to expand left and right forever, so that means the domain is all real numbers because it will hit every x value in existence. And the range will also be all real numbers because it continues to increase to the right and decrease to the left, so it hits every y value in existence, so the range is also all real numbers. So the next example we're going to graph is f of x equals negative x to the fourth plus x to the third plus 2x squared plus x plus 1. So I've already taken the liberty of graphing this one and bringing it onto this screen so we can answer the 4 questions. So the first question is, estimate the x-coordinate of every turning point and determine if those coordinates are relative maximums or relative minima. And I've already highlighted the x-coordinates of the turning points, and there's actually only one x-coordinate of a turning point that's either a relative maximum or relative minimum, and it's right up here. So that is a relative maximum, and the x value at that point is about 1.518. Now, notice that 0, 3 has also been highlighted as an important point. That's actually not a relative maximum or a minimum, because notice that the graph never ceases to completely turn around the opposite direction. It continues to rise very slowly through that point all the way through there. Now, it does turn through those points, but it's not a maximum or minimum because it doesn't turn completely around. Part B is estimate the x-coordinate of every 0. So the x-coordinate of every 0 is going to be where it crosses the x-axis, and the points where it crosses the x-axis is right here and right here. So the x values would be about negative 1.303 and about 2.303. And then it says to determine the smallest possible degree of the function. So remember, we're going to count the number of turning points and then add 1 to that. So as we go through the graph, we have a turn here, so that's 1. And then there's another turn right there near 0, 3, that's 2. So they do count as turning points, even though it's not a relative maximum or minimum. And this is definitely a turning point, so that's 3. And then it continues to decrease to the right, so it has 3 turning points, but we would add 1 to that to figure out the degree. So this is a 4th degree equation. And then it says to determine the domain and the range of the function. So the domain, since it is moving always to the left and shifting always to the right, we would say the domain is all real numbers. This time the range is going to be a little bit different though. The range is not all real numbers because there is a distinct high point on the range. And the highest point this graph ever gets to is this point up here. It never goes higher than that particular maximum point. Well, since the range is based upon the y value, the range is going to be y is less than or equal to, because it is always below that point, whatever the y value is, which is 7.315. Finally, let's do a real-world example. Movies. And annual admissions to movies in the United States can be modeled by the function f of x equals, and then it tells you what the function is with lots of decimals in there because the real world can be complicated, where x is the number of years since 2005 and f of x is the annual revenue in billions of dollars. First part A is to graph the function, which I have already done using Desmos, as you can see on the graph to the right. Part B is determine the turning points of the graph and its end behavior. So there is a turning point right here. And so the x value of that turning point is going to be 0. And there is a slight turning point in here. Desmos didn't highlight it. Again, Desmos only highlights in what they considered important points, which would be maximum and minimum turning points, and since the graph continues to drop, it didn't highlight that as a turning point, but it does turn there at approximately 3. And then there's definitely another turning point where it turns completely around down towards the bottom before it continues to rise indefinitely. So to answer the question, we do have turning points located at 0, at x equals 0. We have a turning point at about x equals 3. That's an estimate. And we can definitely see a turning point down there because Desmos highlighted it at about 7.732. Now, if you didn't have Desmos, you would probably say it's close to 8, and that would be acceptable. And then it says describe the end behavior. So from our last section, we learned that end behavior means what's going on the left and the right-hand sides, and you can see that it is increasing both left and right. The second question is, what trends in revenue does the graph suggest? So the trends in the revenue that the graph suggests is that it looks like the number or the amount of money that movies are taking in has been decreasing for quite a while, starting from 2005. Remember, it says up here that X represents the number of years since 2005. So this point right here actually represents the year 2005. So from 2005 to this point down here, which would be late 2012. And the reason it's late 2012, because if you take 2005 times 7.732, that gives you sometime after July of 2012. So in late 2012, then the revenue at movie theaters started to increase dramatically. So probably late 2012, there was some really good movie out there, excuse me, Avengers, that really turned around the movie industry. So this is an open-ended question, so you could write any sort of sentence or paragraph describing that the amount of revenue decreased from about 2005 to late 2012, and then it increased. And then part D says, is it reasonable that the trend will continue indefinitely, meaning forever? Well, knowing that the end behavior of this graph shows that we'll continue to rise forever and ever and ever on the right side, that means that the movie industry will continue to make more and more money every single year after that. That is very unreasonable. First off, at a certain point, it would likely have leveled out. But secondly, we already know that in 2020, the movie industry pretty much came close to crashing, came to a screeching halt because of COVID-19. So clearly, the amount of money that movies will be making will not increase year after year.